So let's start off with something that we've seen before and we've learned before, the idea of sampling error. So again, we have this population of college professors and college students and favorability of the professors, and that mean population favorability is 3 on a scale of 1 to 5, where 1 is we hate this professor and 5 is we love our professors. And so if we sampled 9 different universities of 100 students each of those samples is going to have its own sample mean. And sampling error, again, is really the difference between each sample statistic, in this case the sample mean, and the difference between that sample mean and the population mean, the population parameter. And so if we're going to take each of these sample means and plot them on a frequency table, on a sampling distribution, we would get something that looks like this. Right, where each of these 9 samples gets plotted and we see a normal distribution and we see that the average of each of the samples represents the population. And so this sampling distribution gives us our mean and also gives us a standard deviation. But this standard deviation is not the standard deviation of the 100 samples with It's not the standard deviation of the 100 individuals within each of these 9 samples. This is the standard deviation of the sampling distribution of the mean from all of these samples within the population. So this standard deviation of 1.22 is really the standard error of the mean. It tells us how much variability there is in the mean across samples from the same population. So here is the equation. Standard error of the mean equals standard deviation divided by the square root of our sample size. And this really gives you an idea of what the standard error of the mean is within the entire population. So here's a visual of what we mean by the standard error of the mean. Looking at the middle distribution curve. Normal distribution, no skewness, not much kurtosis, and we see the mean, really how narrow or how wide our curve is, thinking about kurtosis, really tells us and gives us an idea of our standard error. And so the less kurtosis we have, how flatter and wider our curve is, the larger our standard error, which means we are less precise. Less precise estimate in terms of our sample to our population. And if we go and we see we have more kurtosis, we have a narrower curve, well, we have a smaller error. And this smaller standard error represents a more precise estimate of our sample to our population. And the goal of inferential statistics is to be able to have a smaller standard error. We want to be more precise in our estimation of our sample to our population, so that the more that our sample looks like our population and represents it, the more it estimates it, then the more that we know about really what's going on among everybody, the entire population, not just within our own sample. So click on video 3 here for a thorough explanation and some calculations of the standard error of the mean. It can be a little tedious and a little cumbersome and confusing sometimes, but just work through it, think about what he's teaching you and what he's talking about in terms of standard error of the mean. Again, thinking about this is the standard deviation of all of our samples within the population. Confidence intervals. So confidence intervals is the range of values around a statistic, such as the mean, that are believed to contain with a certain probability the true value of that statistic. So really, in other words, how confident are we in our estimation of our statistic to the parameter? And so the middle, as we know from a normal distribution, that the middle is where the mean is at. So this is also known as our point estimate. This is the middle of the confidence interval. And so this is the sample mean is our best guess of the population mean. We have a lower limit, which is the lowest value of the confidence interval, which is to the left side of our normal distribution curve, and we have an upper limit, which is on the right side, which is the highest value of our confidence interval. And again, thinking about our confidence interval, this is really the range of values where we think the real population mean exists. We have our mean, which is our best guess, and then we have our little buffer zone, which is our upper and lower limit. And really, the margin of error is the distance between our sample mean, which is our point estimate, and the distance between that point estimate to the lower limit, which also equals the same distance between the point estimate and the upper limit. And so another way that we can look at this confidence intervals in terms of looking at the normal distribution and point estimate, margin of error, lower limit, is with the dot and line. And we see the dot represents our sample mean, and the lines represent our margin of errors. Again, our sample mean is our point estimate. Sometimes you'll see parentheses, blue parentheses representing the lower limit and upper limit, or you'll just see just the line, which represents the size and the length of the margin of error, and you just know that the end of the margin of error contains your lower and upper limit. Here we see the formula for confidence intervals. So we know that we have x bar, which is the mean, and then we know that because we have an upper and lower limit, our mean plus or minus z-score times standard deviation over square root of n. And we see this last term, standard deviation over the square root of n, is the standard error of the mean. So one way that we can think about and write out and say what our confidence formula is the mean plus or minus our z-score times the standard error of the mean. And so again, thinking about this and knowing what makes up the formula, how big or small the confidence interval depends upon the sample size. The larger your sample size, the smaller your confidence interval. I'm thinking way back in part 1 video when I talked about how our sample size really tells us much about our significance. It really tells us if we have statistical significance or not. Well, our sample size, the bigger our sample size, the smaller our confidence interval. And this is because we have more confidence that most often a smaller sample is more representative of the population than a smaller sample. Right? That makes sense. If you only have 10 people in your sample out of a population that contains 300 million compared to a sample of 10,000 or 1 million, well, the bigger the sample size, you're going to think that, yeah, they're going to look more and more like the population. Another thing that the confidence interval depends upon in terms of its size is the percent confidence interval that we want, which is related to our z-score. So the bigger our z-score, the bigger our confidence interval. And the more confidence that the true population mean is somewhere within that confidence interval. So thinking about our normal distribution curve that we talked about last week, we know that underneath that curve, we have z-scores, we can put our raw scores, we can plot our standard deviations, and we know how much probability and how much percentage falls underneath fixed proportions of that curve. And so when we'll talk about our 90% confidence interval, that corresponds to a z-score of 1.65. A 95% confidence interval corresponds to a z-score of 1.96. And a 99% confidence interval corresponds to a z-score of 2.58. So one way you can check this out is I encourage you to take a look at your z-score table and look at the z-scores for each of these confidence intervals, 1.65, 1.96, 2.58, and look at the proportion, look at the probability that it corresponds to, and see if it makes sense. And then the last thing that determines how big the confidence interval is the variance, or standard deviation. How much variability is there within your sample? The more variability there is, larger the confidence interval. Again, this is because more dispersion, more variety of answers means that not as many people in the sample have scores that are close to that point estimate, that are close to the sample mean. Right? The bigger your standard deviation, the more variability you have, which means that you're going to have a bigger curve. Right? You're not going to have, they're going to be more dispersed, more further away as opposed to very close and tight-knit to that mean. Thinking about kurtosis and how peaked or how wide the curve is. So the margin of error determines the width of a confidence interval. Thinking about our equation, we have the mean plus or minus the z-score times the standard error of the mean. That term after the plus and minus is our margin of error, and that determines how big or how small the confidence interval is. And so really the margin of error takes into account the sampling error because it's part of it. So let's look at this example here, this diagram. We had a student ask them about their favorability of their professors. They gave their professor a 4. Well, in one particular sample, one university of 100 students, their sample mean was 3.75. When in reality, the average of the population was 3.72. So knowing this, and knowing that sampling error is really simply the difference between a parameter and our statistic, the sampling error in this case is 0.03. It's simply the difference between 3.75 and 3.72.